So the next type of calculation we're going to look at is a mass-to-mass calculation. This is probably the most common calculation that we ever do in chemistry, and it involves using two conversion factors. We're going to use 2 molar masses, but we're also going to use 1 mole ratio. So in total, we're going to have 3 conversion factors every time we do one of these guys. 2 of them are of the same type though, and 1 mole ratio. So 2 of them will be molar masses, and then we're going to have 1 mole ratio. So these are not too tricky once you realize that they all follow the same pattern. So what we use molar masses for are to convert between grams and moles of a substance. So here we are, I'm going to take grams of something, and we're going to turn it into moles of something. We can take grams of something else, turn it into moles. And of course we can go back the other way, can't we? We can take moles of something and we can turn it into grams of something. To convert between moles of one thing and moles of another thing, we use a mole ratio. And the mole ratios are going to be obtained by looking at the coefficients that we have in balanced chemical equations. In this section, we're going to be looking at a very common chemical calculation, which is what we call a grams of A to grams of B type of calculation. And this will always involve 2 molar masses and a mole ratio. So yeah, it's going to be pretty easy, and what we're going to do is we're just going to go from grams of one thing in our chemical equation over to grams of another thing. And it could be any two, right? It could be methane and O2. It could be, O2 to CO2. It could be any two. They could be on the same side of our chemical equation. They could be on opposite sides of our chemical equation. We might go from products to reactants. We might go from reactants to products. We might go between products. Just any two things that happen to be in our chemical equation, we're going to be able to go from grams of one to grams of the other. So here's a good example. It says if 64.2 grams of methane is reacted, how many grams of O2 must be reacted? So we pretty immediately recognize this as being a grams of A to grams of B. So this is kind of like saying, I've got a dozen eggs and I've got a pound of flour. How many cookies can I make? Right? This is the kind of calculation that you might be doing. Or, I've got a pound of flour. How much milk am I going to need to go with that if I want to make some brownies? All right. So in this case, we've got 64.2 grams of methane, and we want to know how many grams of O2 do I need to go with that. So what I know is this is a mass of A to mass of B, so I'm going to need molar masses of both of the components. I'm going to need the molar mass of methane, and I'm going to need the molar mass of O2. So to get the molar mass of methane, I take the mass of 1 carbon, and then I add to it the mass of 4 hydrogen atoms. So there's my molar mass of my methane. So I got my molar mass of my first guy. This is my A, all right, what I'm starting with A. Now I need my molar mass of my O2. Note that I don't include that coefficient, all right? So the molar mass of the O2, in every O2 there are 2 oxygen atoms that have a mass of 16 grams per mole each. So this is my B, all right? And then finally what I need is my mole ratio that relates my moles of A to my moles of B. And so I'm going to get that from my chemical equation, and you can see here I get 2 moles of O2, or I need 2 moles of O2 for every 1 mole of methane. So now I've got to put it all together. I'm going to begin with my grams of A, my mass of A. So it's 64.2 grams of methane. That was given to me in the problem. Then I have to multiply that by its molar mass to get moles of methane. So I know that in 1 mole of methane, I've got 16.05 grams of methane. I want to make certain that I've got that correct. Yep. So now I'm there. So that's good, right? Now I've got to multiply this by my mole ratio, and I want to be going towards moles of my B. So I want to be going towards moles of A, moles of O2. So I get 2 moles of O2 for every 1 mole of methane, and I can see that that has worked because now I have my moles of B. And then the final thing that I need to do is to multiply it by my molar mass of my B, which is 32 grams of O2 for every 1 mole of O2. And then that will cancel out my moles of O2, leaving me with what I want, which is my grams of O2. So I feel comfortable about going ahead and doing this calculation now. And so 64.2 times 1 on 16.05 times 2 times 32. I'm going to put all of that into my calculator. I end up with 256 grams of O2 are needed. I rounded my answer off to 3 significant figures because the data that was originally given had 3 significant figures, and I'm only doing multiplication here, and I know that my rule for multiplication and division is that my answer needs to have the same number of significant figures as the measurement with the least number of significant figures. It should be noted that mole ratios are exact numbers, as they are the number of items of something, so they are exact numbers. All right, let me see. This should say can be produced because it's a product. All right, if 64.2 grams of methane is reacted, how many grams of CO2 can be produced? And again, this is a grams of A to grams of B. So I know I'm going to need my molar mass of methane, and I'm also going to need my molar mass of CO2. So I went ahead and calculated that. For methane, it's just the mass of a carbon plus 4 times the mass of a hydrogen. And for CO2, it's the mass of a carbon plus 2 times the mass of an oxygen. So there are my 2 molar masses. Now I need the mole ratio that relates moles of methane to moles of CO2, and it's very simple in this case. I get 1 mole of CO2 for every 1 mole of methane. So now I've just got to do the calculation, right? So it's going to be the grams of methane multiplied by 1 on the molar mass of methane, and when I do that, that gets me to the second box here, which is moles of methane, because methane is my A and carbon dioxide is my B. Now I'm going to multiply by my mole ratio, and I want to be getting rid of methane, and I want to be left with O2. So multiplying in that way gets me to my moles of B. So I only have one last conversion to do, and that's to take my moles of O2 and turn it into grams of O2, and to do that I'm going to multiply by the molar mass. So the molar mass of CO2 is 40, that should say CO2 there. The molar mass of CO2 is 44.01 grams of CO2 for every 1 mole. So that's going to cancel out my moles of CO2, leaving me with grams of CO2. And again, I rounded to 3 significant figures because the data that I had been given was given to 3 significant figures. So it's the same every time. Multiplied by 1 on the molar mass, multiplied by the mole ratio, multiplied by the molar mass. All of these calculations are exactly the same. So grams of A to grams of B is pretty straightforward once you recognize what's going on. You need both molar masses and a mole ratio. Okay, so let's have a look at some ALEKS topics on this. These are a little more difficult because you have to come up with your own balanced equation. But if you use an online equation balancer, it's normally pretty quick. So it says ammonium perchlorate is the solid rocket fuel used by the US space shuttle. It reacts with itself to produce nitrogen gas. So when we say it reacts with itself, that means really what we're saying is that there's only one reactant. And then it says to make nitrogen gas, chlorine gas, oxygen gas, and water vapor, and a great deal of energy. So what I want to do is I want to balance it, and I think that's like what's obvious here is that the nitrogens don't balance, do they? Because I've got 1 on the left and 2 on the right. So I'm going to want at least 2 of those guys. Now let's move on and check the hydrogens. So on the left now I've got 2 times 4, that's 8. And then on the right I've only got 2. So I'm going to want 4 of those. There we go. So that's going to be helpful. And now I've done the hydrogens, it's looking good. Yeah, so nitrogen and hydrogen's gone. So now I'm going to move on to chlorine. And on the left I've got 2. And on the right I've also got 2. So chlorines are done. And so then that's just going to be oxygens. And on the left I've got 2 times 4, that's 8. And on the right I've got 4 plus another 2, so that is 6. But hopefully you can see that if I just make that a 2, then I would have 8 oxygens on both sides and everything is balanced. So let's have a look at this now. We've got 2 ammonium perchlorates reacting to give 1 N2, 1 Cl2, 2 O2s, and 4 waters. And we can't get a smaller set of coefficients because we can't divide through by a common multiple. Now the question is asking what mass of oxygen gas is produced. So the answer that we want is going to be in grams of O2, given that we're beginning with 9.35 grams of ammonium perchlorate. So that's 9.35 grams. So I know that what I need to do is this. I need to go from grams of ammonium perchlorate to moles of ammonium perchlorate. And then from there, I'm going to go moles of O2, and then I'm going to go grams of O2. So that's what I'm going to do. So I need 2 molar masses. I need the molar mass of ammonium perchlorate, and I also need the molar mass of O2, and I need my mole ratio. So let's just get going on, and then my answer is going to have 3 significant figures. So I got 9.35 grams of NH4ClO4, and I've got to multiply that by 1 on its molar mass. So I get 1 mole of NH4Cl4, and I'll calculate this in a moment for every however many grams of ClO4, and then I got to multiply that by my, so that's going to get me to there. Then I got to multiply that by my mole ratio, and according to this, I get 2 moles of O2 for every 2 moles of ammonium perchlorate. So 2 mole of O2 for every 2 mole of ammonium perchlorate. That's good. And then finally, I've got to multiply it. So that gets me to there. I've got to multiply it by the molar mass. So I get however many grams of O2 for every 1 mole of O2. Okay, so I need to get my 2 molar masses. So my molar mass of O2 is pretty easy. That's 2 times 16.00. So that gives me 32 grams per mole. And then we've got to do, finally, we've got to do our molar mass of the ammonium perchlorate, which is a little more complicated because we've got 1, 2, 3, 4 different types of atoms. So my molar mass of ammonium perchlorate, we got 14.01 for the nitrogen, and then we're going to add to that 4 times 1.01 for the hydrogens, and then we've got 35.45 for the chlorine, and then finally we've got 4 times 16.00 for the oxygens. So we put all of that together. What do we get? 14.01 plus 4 times 1.01 plus 35.45 plus 4 times 16, and it's going to be quite big, isn't it? It's 117.5 grams per mole. Okay, so that's really it. So that's 117.5, and then that is 32. So moles of O2 cancel, moles of ammonium perchlorate cancel, grams of ammonium perchlorate cancel, and the only thing left is grams of O2. So I can go ahead and put all of that into my calculator, confident that I'm going to get the correct answer. So here we are, 9.35 times 1 on 117.5 times 2 on 2 times 32. My answer ends up being 2.55 grams of O2. There we go. So that's it. That's the maximum amount of, or the amount of O2 that I can make from that reaction. So it's always the same, 2 molar masses, 1 mole ratio. So whenever you're doing a mass of A to mass of B calculation, it's always going to be multiplying by 3 conversion factors. 2 of them are molar masses and 1's a mole ratio. Okay. So that concludes this section on mass to mass calculations, and I hope you found the video helpful.